Hey, hey, hey! Welcome back to the virtual shop, boys and girls. Today, I want to get back to the roots of everything in the universe, physics and chemistry. So, it's kind of a fun little show we're going to do today, but it will tie in and relate to tuning at the end. So, this is really just, for kicks. This is what I like to do, think about anyway. So let's talk about what plasma physics has to do with boost. And I know I normally do NA oriented stuff, so this is breaking a little bit away from my normal stuff. But plasma, we're all familiar with solid, liquid, gas. Plasma is the fourth state of matter caused by superheating it and ionizing a gas, and that gas then becomes very conductive to electricity. So on a vehicle, you do have a plasma generating system. The energy comes from the ignition coil over here. The spark plug is really just the conduit for that energy with a controlled little gap. That spark is the plasma right down there. So all plasma physics, well, maybe not all plasma physics, but the master, the maestro of plasma himself is Nikola Tesla, my personal fan favorite of all time, my favorite scientist, inventor, engineer. I love this guy. He is the crown jewel of all the Victorian era scientists, in my opinion. After his era, everything went to corporations for profit and colleges, but either way, you had teams of people working, right? Prior to the Industrial Revolution, it was like you had one guy who had some spare time and he was just dinking around, pouring stuff together, seeing what happens. Um, and so Tesla, and in my opinion, is we owe a huge debt of gratitude to him. All of our modern society for power electronics, everything, all stems to this guy. In my opinion, others may disagree. Whatever. You're wrong. Just kidding. But of his numerous inventions, he invented a high voltage, high frequency, loosely coupled air core resonant transformer. It's kind of a mouthful. We just call it a Tesla coil. And that was invented in 1881. And if you think about this time frame, this is pre-industrial revolution. The average person had never even heard of electricity. They didn't know what it was. And then you have this guy who seems to have mastered everything electrical. That foundation or that circuit is the foundation for radio, later stolen by Marconi. Unfortunately, the Supreme Court overturned that and gave Tesla, uh, you know, as the inventor of radio. This is what I'm talking about. This is in Tesla's Colorado Springs laboratory in 1899 through 1890. He was filling up an entire room full of man-made lightning, right? He had it figured out. Now, this is a double exposure. That's, he's not actually sitting there. And I will point out a Tesla coil does not break the laws of physics. It does not create energy. It does not amplify or create energy that isn't there. It's not a free energy device. It's physics and operation completely and 100% obey the laws of conventional physics. I am not trying to tell you some of the crazy stuff that you'll see about how Tesla coils are a free energy device. They are not. Just a couple more pictures. Again, filling up a room with lightning, man-made lightning at will and easily in that era was just unheard of. I was inspired by it. I built my own Tesla coils. I would say this coil here at Colorado Springs, probably the largest one he ever built. He did after he left Colorado Springs, he went back home to New York and he built the Wardenclyffe Tower. And this was actually going to transmit energy. Probably was a bigger Tesla coil, but I don't think he ever fired it up, although there are rumors that it was. But I will say the Colorado Springs lab coil was the biggest one ever made. I built my first one in 1999. Pretty simple. Started off with salt water, beer bottle capacitors, which I later upgraded, blah, blah, blah. I won't bore you to death. But I think at its peak, was able to produce 21 inches of spark. This, these pictures were taken on 35 millimeter film camera. If that tells you anything. Built the last one here. This is in my current garage. um, and significantly larger coil and larger power input. This orange ladder is a 12-foot tall ladder. And so this spark, if we measure from this point to this point, is 75 inches, negating all the twists and curves, right? That comes out to 75 inches, just over 6 feet long, which I think is like what, 2 meters plus or minus. I don't really know. So this bolt of lightning here, this arc is plasma. We have superheated the air and it has become very conductive and electrons can freely flow and move to there. This is that same coil, but it's with a 10-second exposure. So you can see there's all kinds of Silver Surfer made lightning flowing through the air here. And then I made this one on a whim one night. This is a precursor to my next one. It's a 3 coil system. We have a primary, a secondary, and then this transfers over here to this tertiary coil. This is a 2 coil, right? You have the primary down here. It's like a flat pancake coil, and then the secondary goes up here. So this is the test bed for my next one, which is going to, as things progress, right, bigger, better, more power. So this is a power distribution transformer that the power companies use. So 10 kVA, like 10,000 watts, and will output 14.4 kilovolts to the Tesla coil system itself. I'm hoping for 10 to 12-foot arcs. That would be an outdoor operation only, as you can imagine. All right, so let's get back a little bit more to ground here. No pun intended. But Tesla was kind of the first one. I won't say he was the first one to realize that you could produce light from high voltage and gas, but he was the first one to put it to practical use. So he came up with this system for lighting, electrical lighting, and this was unlike the Edison bulb, which used filaments of tungsten or whatever that glowed red hot and were extremely inefficient. So this actually used um, high frequency, high voltage, and it produced glowing light from the gas. And you can look up this patent if you want to. Um, and then later, this guy was like, "Oh, well, I'll just use that same idea and we'll just call it a neon light." So, and then other people went on to use the same idea to create fluorescent lights. But, you can see we have the Giesler tube and the Crookes tube's not listed in here, but Tesla loved William Crookes and the Crookes tube. But either way, you can see gas discharge lamps with phosphorescent coatings. That's a fluorescent light. Now, I guess these guys probably made it where they could run on low voltage, but all right, let's get down now to a little bit more details. This thing called Paschen's law, and all this is saying is that sure, you can ionize a gas, turn it into plasma with voltage if you have enough voltage, but as you start putting it under a vacuum and pulling out pressure, you need less voltage. It becomes very, very easy. So we have some various gases. We have some noble gases up here. We have hydrogen, which is diatomic, and nitrogen, which is diatomic. They're not noble gases, but helium, neon, and argon are. And you can see they all tend to follow the same trend, and they keep going down and down, and they each have their own sweet spot of the lowest, right? As you put it under enough of a vacuum where you need very little voltage to make that work. This is the equation this voltage breakdown. This guy right here, this term, this is the secondary emission, electron emission coefficient, and it's our wily devil. And this is probably why we cannot just go to a calculator to calculate what we need with the spark plug when we're under boost. Because all this is saying is that when you have that plasma channel and things are going crazy, there's going to be some other factors, moisture in the air, even maybe oil from the oil filter, but also the electrodes themselves. Platinum, iridium. If you have a copper plug, well, the electrodes aren't copper, they're nickel plated, but each one of those is going to have a vastly different coefficient down here, so it makes it a little bit unpredictable. You can see ln, these are logs. These scales are logarithmic. If you notice these um, hash marks for the axes, are not linear, they are logarithmic on both axes. So let's look at what happens inside the combustion chamber. So we have this little shorty spark plug and one electrode here, one electrode, and this is our combustion chamber. So our combustion chamber is filled with some type of gas. Well, really that's just plain air, round numbers, 80% nitrogen, 20% oxygen. Maybe you're spraying a little bit of nitrous, and that's also gonna have its own Paschen's curve. And then when you start mixing different gases, so on and so forth, it's going to change. We also have the voltage, right? So most LSs, if I recall, the coils are going to be producing about 40,000 volts, right? And then we also have the gas pressure. And this is, kind of the wily devil here, right? We'll talk about that in a second. And then we also have the plug gap itself. So we can't really change the atmosphere that's coming in here. So I've labeled that as fixed. The foils are fixed. Now, yes, you can buy aftermarket foils, but I don't know the feasibility. Most people have found that aftermarket foils don't last very long, therefore just run stock ones. But also, we're given the choice of our solutions, spending $500 to $1,000 on some coils may not be the best option. So most people aren't going to change the coils. And maybe they do make some 80,000 volt coils or something like that. But now you run into the issue that you may be causing some extra line noise that's going to interfere with the ECM. So it's just best to stick with old reliable stockers. So the gas pressure, this is going to be variable. So as you start throwing more and more boost at it, well, that pressure goes up. So then what is our other option is we have to change the spark plug gap. So in the end, the question is, do I have enough voltage to form an arc, ionization channel, to create plasma, whatever, in this amount of distance in this pressure? So let's look at an example. So here is a typical Paschen's curve. This is actually for air. I've removed the units, right? This is just conceptual here, right? So our ignition voltage is fixed, right? So we'll assume this is 40,000 volts. So we buy our car, it's stock, it's naturally aspirated, stock compression ratio, whatever, but we're NA. And we can see that for this pressure, we are underneath the threshold for how much voltage is needed to bridge that spark plug gap. Everything is fine. Well, the engine blows up, our rich uncle dies, leaves us with some money. First thing we go out and do is buy a supercharger. We throw a ton of boost at it. And now we have a problem, right? You can see that we are over the line, right? We do not have enough voltage to bridge the spark gap. We are higher up on Paschen's curve. So our solution is, well, we can raise the ignition voltage, right? So that it is higher than this spot right here. As discussed before, that's really not feasible in most cases. So our next solution is to attack it the other way, which is just reduce the spark plug gap, which will then put us lower on this curve, but more importantly, underneath this ignition coil threshold, or I should say ignition voltage threshold. So when we start looking at different applications for this, neon signs are pretty low. They're lower than 1 kPa. Fluorescent tubes are pretty similar, 1.5 kPa and lower. And just for reference, your typical ambient air pressure is, well, where I'm from anyway, 96 to 100 kPa. I did just come back from Santa Fe, New Mexico, 7,200 feet. We went up on a mountain at some point. We were at like 7,400 feet above sea level, and it was checked my phone app. We were down to like 76 kPa. Yeah, man, the fat boy was wheezing up there. All right, so this is the fun part. We're gonna go into the high voltage laboratory, well, aka my garage, and we're gonna do some hands-on practical demo. So button up that top button, tuck in those shirts. It's time to be professional. Okay, so for our first demo, we'll just keep it simple. I have a regular transformer here, iron core, copper windings. You can see it's 6,500 volts out, 20 milliamps output for a total of 130 K, or not kVA, but just VA. Over here we have some improvised spark gap I made years ago. I don't remember exactly what I was trying to do, but either way, that's two tungsten welding rods ground to somewhat of a rounded edge, and then some copper holders. So this is just in my garage, obviously open air. Ambient pressure is 99.4 kPa. This gap is as big as I can reliably get to get 6,500 volts to jump it. This is about 1.3, 1.4 millimeters, which is just over 50 thousandths of an inch. So let's see what happens. Firing the apparatus in 5, 4, 3, 2, 1, contact. Isn't she beautiful? Okay, enough of that. Okay, so now we have the same arrangement electrically with the same 6,500 volt transformer. We'll move that out of the way, but we have now connected it to just a little holder for a neon tube. Now this overall length from electrode to electrode internally is like 17 inches. So we'll just snap this into place. And we'll go douse the lights and we'll fire her up. Hold on. All right, so now we've gone from 99.4 kPa ambient to 1 or less kPa. Plug it in and boom, we have a neon light, and it has no problem traversing 17 inches to make that whole distance. So obviously it would be nice if we could go the opposite way, if I had a way to safely pressurize some ambient air and see how much more voltage it takes to jump the same distance, or how much I have to close a spark gap to jump the distance. But either way, you can see that less pressure in gas means it can traverse, the voltage can traverse more distance. All right, well, let's try something a little more spicy, why don't we? Just a quick warning here, not only will it kill you, but it's going to hurt the entire time it's doing it too. So only befitting that we have the maestro himself, Nick Tesla, watching over us, making sure everything goes smoothly. So we're going to do some Tesla coiling. Well, this is just for size purposes. That's a 6-inch PVC pipe. That is a picture of the coil that I showed you earlier that was making over, I don't know, like 75 inches of sparks. We're actually going to be using this little dinker here. I got off eBay. Maybe it was Amazon. I don't remember. But it was too cheap. I was like, I can't remember. $2-3, maybe $5 at the most. I 3D printed a little stand. It just runs on 2 transistors. 20 volts on the input and like an amp or less for the supply side. So let's see what this thing does. So first thing, we can see that it is able to produce a little bit of plasma in just plain air. It's, you know, less than 1/4 of an inch, just a few millimeters. Nothing spectacular, but nonetheless, it does what it's supposed to be doing. So there is proof of that. Okay, so let's apply some power here. Contact. Now, we have that same neon tube here. If I place it right in the middle, you can see the whole thing lights up. We can apply it just to one end, and you can see, maybe if I move this a little bit like that. I'm going to try zooming out just a little bit. You can see that it kind of, I can't really hold it steady here, but you can see that it travels up, not all the way through the tube, but most of it. And what happens if we use a regular a new school compact fluorescent light bulb? Like, I'm not even touching it, right? It's just in the electrostatic field and it starts to glow. And what about a black light? Very cool. Like, again, I'm not even touching it. We're just kind of getting in the vicinity and it'll start to glow. Boom. Fire and ice, baby. And let's see, I also have another tube. This is from like a 1980s or 90s photocopy machine. And if I do it here, nothing really happens. I'm physically touching that plasma. But if I do it this way, let's see if we can zoom in. This makes like little individual streaks like a plasma globe. Let's see if we can get it on here. Maybe not. What happens here? There we go. So you can see, wish I could hold it steady. It'll go to my finger and it'll go even further. So again, that weak little plasma stream, open air, will definitely jump. And this is about that same size, 14. Actually, I think this is a little bit longer tube, maybe 18 inches or 20 inches total length. But there you go. All right, one last demo before we go. This is a normal transformer for neon signs. It's kind of hard to read. Looks like someone scratched it out, but this is 15,000 volts at 60 milliamps. So I want to show you one other thing. I believe I've demonstrated at this point we can extinguish a spark or, take advantage of it, make it bigger or smaller by changing pressure. But what about airflows? Now we got some spicy guy here. If I take my air compressor, sure enough, I can blow it out with air. One more thing. So this is just that little Tesla coil hooked up to the tube. I have a rare earth magnet here, and you can see that plasma is reactive to magnetic fields. What do you think? Should we put some magnets inside of spark plugs and sell those as the new hot stuff? Wow, wasn't that fun? I certainly had a fun time. I hope you learned something out of that and got to see some cool stuff that you don't normally see. So, in the end, um, all this boils down to, I guess, all the posts I see on Facebook or the forums, right? It's like, oh man, my blower's blowing out my spark. I got too much boost. It's blowing out my spark. And that's not the case, right? We call it a blower. I suppose that's the cool term, but they're compressors. All they do is they compress the air. They change the density of the air going into the cylinder. It's not wind. It doesn't blow things, right? And this is actually, I've found this Ford. How bad does this Ford guy have to lose that he's got to put a Chevy motor on it with two blowers? Anyway, this is my son. We were at a car show, and this is a pretty cool car, I'll admit. A lot of customizations, but yeah, man, two blowers, come on. So either way, it doesn't matter what kind of compressor or blower you're running. They all do the same thing, right? They compress the air, and it's the pressure of the air. It's not the wind that is quote blowing out your spark. So maybe don't say my blower's blowing out my spark, right? Maybe just say I boosted my spark out instead of blowing it out. I don't know. I guess blowing out your spark is the cool guy way of saying things, which is what I've struggled with my entire life, being cool. Mm. Anyway, so next time you see something like that, you can educate them about Paschen's law and what it takes to ionize a channel of plasma at a given fixed distance per pressure. Be the hit of the party. Well, anyway, appreciate you watching, and I'll check you next time. See you in the winter circle. Later.